today. His title is up there, and I guess that this is a lot of your PhD work. Thanks, Tola.
Thanks, Judith. Welcome, everyone. Like Judith said, it's part of my PhD thesis, and major work was done focusing on the field and thin section description for the Rooiberg group. However, in this talk, I will also show part of what I'm doing now and what I hope to do in the nearest future. For my PhD, I described the lithophases and did some geochemical work on the Rooiberg group. And as you can see in the picture, that's one of the best exposures of the Rooiberg group, where a lot of the physical features that I'll be talking about today are well preserved and well exposed. Inset there, you can see where I am here, as little or big as I am. So the Rooiberg group is part of the well-renowned and well-studied Bushveld province. And instead, you can see the different lithologies, but more importantly, the Rooiberg group in dark colors, which is found in the Bushveld province. And these three squares there mark the areas that I mapped, for which geochemical maps were created, just to see if anything that has been missed by the well-studied area from previous researchers is found or observed. And this reason is because the Bushveld, as you can see, is one of the largest and the oldest province, which is petrogenetically linked with the Bushveld magmatic province. And though it's linked, it's still described, and even up to recent times, as the volcanic end to the Kaval crater. Last week we heard about why we do studies, why we do research. It's always an important thing to have a focus. I started this journey because I realized that though Bushveld is unique, important, and probably one of the largest, but the origin is still not well, how do I put it, accepted, or we don't have a unanimous decision, unlike other silicic provinces around the world, like the Kevinavan or the Yellowstone. And these two theories are what dominate the origin of the Rooiberg group: the subduction-related theory and the partial melting that majorly represents the fractional crystallization and assimilation by a mantle-derived liquid. Why is it that these two theories come after, once in a while, and people support one over the other, or at the end of the support for one theory, they always go back and say you cannot rule out subduction-related related processes? We'll see that as I go along. This picture, I like putting it up because the stage I am now in my postdoc, the intrusion of the Bushveld, the Rosenberg layer suite of the Bushveld province is actually going to play a major role in understanding the Bushveld magmatic province, in the sense that we have similar ages between the Rooiberg group and the Rosenberg layer suite, but we always say similar. How similar? Are there any differences, even if it's just a few million years? This will give us an idea of what the origin or the source of these liquids, of these rocks are. So to go straight into the areas mapped, we did work on the Dahlstrom area. And one important thing I would just like to show is that the Dahlstrom is made up of just one formation of the Rooiberg group. As you can see, it's made up of 4 formations here, and this is the oldest, lying beneath as well as above the Rosenberg layer suite. And though it's made up of one formation, it has different magma types as described by previous studies, especially in the works of Schweitzer and Buchanan. One important and interesting thing is just the occurrence of rhyolites at the base of the Rooiberg group. This has really not been focused on by previous people, and that's where part of my work lies today. In the Dostrum area, we mainly have reddish-brown rocks that go into gray colored rocks, which dominate the Dostrum area. However, we still have some amygdales, which can be as large as 1 centimeter. And this, though occurring throughout the sequence, is somewhat confined to the gray lavas in the Dostrum area. Within the Loscope area, we mapped 2 different parts, which was based on the farms that we are allowed to go into. And these farms, one is a bit northeast of the dam, while the other is just southeast of the first area. And in this area, we found it very suitable for Rooiberg research because it contains most of the formations within the Rooiberg group, which we can see as displayed in the maps. The Downward Formation, the Quackersneck Formation, and the Skriklu Formation. And the other area that we mapped close to the Loscope Dam, we have the Damval area formation and the Quackersneck Formation. And this area was a bit troublesome because we have high and steep mountains that has thick vegetation, and also this vegetation have really caused erosion of the surfaces that we would have required for proper field studies and observation. Examples of the rocks you find in there, and this is a very unique one that we were fortunate to see, that contains spherulites that have been somewhat grown into lithophacy, which usually has a rim of that is filled with plagioclase, feldspar, and sometimes quartz. And in the bottom part, a thin section just illustrating the dominant feldspars and quartz in these rocks. This last area of study, which is the Modimole area, visited by some of the lecturers in this department, is still under construction, as a lot of things are being observed which have not been reported before. So I won't say much about this. So after observing, making thin sections, investigating the properties of these rocks, we started seeing features that were not really pronounced in previous studies. And these features made us ask the question, are we really dealing with lava, as previously talked about, all felsites, or are we dealing with Ignimbrite? And we had to now define the difference or differences between lava and Ignimbrite. And I've put up a few points that I can easily support with evidence from the field, especially from the Modimole area that I showed earlier, where a lot of these features are still preserved and visible. With regards to the lava, you have a basal breccia, while in the Ignimbrite you have an upper breccia. This, though not visible in the picture I showed you at the front page, is very important in the classification of the Rooiberg group as lava, as against, as Ignimbrite against lava. And other point is the fact that we have a lot of broken crystals within Ignimbrite. This you hardly find in lava. Another important characteristic of Ignimbrite is the fact that you have flow structures such as oblique folds, sheet folds, and these really define the boundaries between the lava and the Ignimbrite, as these flows are actually absent in lava. Last but not the least, we have the geochemical classification of Ignimbrite and lava, though I'm still cautious about this, but we have low niobium and zirconium opposed to the high one for lava, which we will see in a few slides. So to support which aspect the Rooiberg falls in, I'm showing you evidences of those points I just mentioned in the form of top breccia that we see, and this is part of the area that I stood on in the front page, in which you have the top breccia, and this breccia grades from welded to non-welded and so forth until you get to the unwelded. Some of these class within the welded parts can be as large as 7 meters across. For example, you can see this breccia there, which is, I can tell you, is not the largest that you see in the Rooiberg area. And this is also exclusive to the Strickland formation. By this, we definitely know now that it's the top breccia, and this supports the fact that it can be classified as an Ignimbrite. In terms of broken crystals, there are ton of broken crystals within the Rooiberg group. And here you can see, for example, some of the vitrified matrix that has been recrystallized or filled with secondary minerals such as epidotes and chloride. But of importance is the cosphate glass shards, which, though evident in the low scope area, is not as pronounced as you see in the Modimolle area, where you have glass shards that have been broken apart and stretched, possibly along the flow axis, and these are typical of Ignimbrites. Also here we have, pardon the bad picture, but we have flow bands, which though is also found in lava, but you can also find it in breccia. However, you can see the flow bands causing the glass shards to stretch, like I talked about earlier, within the flow structures. And sometimes you have a bit of quartz veins, which have been described as typical of the Rooiberg group, though more pronounced in the upper part than the lower part. And one other important thing is, in the upper part, it's much thicker than you find in the Dahlstrom area. Niels and I saw a structure that he, with his experience, was able to easily tell me it's a Bujinach fiam. However, the first time I saw it, I had a discussion with him and said, can this thing actually be a property of lava? And because he was not in the field with us, he asked me, how do you mean? He said, I'm seeing things that I read in journals, materials that actually support the formation of an Ignimbrite. And it was until that point that he started saying, okay, we have to go back to the field together. And this just confirmed that what we are working on is actually an Ignimbrite, because you hardly find structures like the Bujinach fiam in lava flows. You mostly find them in Ignimbrites. Another interesting thing you find in the upper part of the Rooiberg group is what we call the sheet folds, like the flow structures, where you have flows that are beginning to form blocked by another fold, forming angles, and they form the eye structure that looks almost like an ellipse kind of structure. And these you can only find, or has been described to be found only, in Ignimbrites. And finally, the geochemical aspect, where you find the Rooiberg group plotting in areas with the low niobium and zirconium region that further supports that you're dealing with Ignimbrites. So the question comes, now all these things I've mentioned, especially with the physical features, are more pronounced to the upper part of the Rooiberg group, which is the Scrickle Formation, which the youngest, the Quagga Snake, and the Damvar. Does this mean that the Rooiberg group might be divided into two? Is the Dostrum really, really different from the upper three formations? So this brings the thought that what we have been describing as lavas, felsites, are they really just Ignimbrite? In other words, are all rhyolitic accumulations on the surface of the Earth Ignimbrite? That we're not sure about, but it seems so, because we have the likes of the Yellowstone that are also called Ignimbrite now because of the structures and the features they possess. And also, is the basal Dostrum formation, like I said, different from the overlying? And if they are different, there should be some more evidence. And in that case, I started trying to check for geochemical evidences, or evidence, whichever one I see. And this increased the way I played with my data, the way I read through, and for a start, I did a chemostratigraphy of the Rooiberg group in the Loskop Dam area, and I looked at how the elemental composition changed with depth. One thing that you can easily see is there's a trend that somewhat supports differentiation, fractional crystallization, going from a mafic region to a more silicic region. For example, you have the high titanium going into low titanium. We have the low silica going to the upper silica. The only elements that may not necessarily show a change are the alkalis, which is ubiquitous to the total region within the Rooiberg group. So now we see that we support possibly the second theory of Rooiberg evolution. There's fractional crystallization pronounced. And though this area excludes the Dostrum formation, we know that the Dostrum formation is more mafic, so it probably will plot easily to show, also to support, further support a change from a mafic to a silicic composition. Another result I got is plotting the classification scheme, but not using the total alkali silica scheme now, but using the mobile elements and ratios, which help proper classify boundaries within geochemical suits. And here you can see that there's also a trend moving from a mafic within the older part to a more silicic within the younger part. However, I don't know if you're able to notice something fishy about this picture here from one of the slides I showed you earlier with the maps. You can see that the basal formation, the Dostrum formation, does show that we have rhyolites. But in this picture, I don't know if you can see that it doesn't show in there. And this actually woke me up because I was sleepy when I saw this, and I said to myself, is my data wrong? Did I get anything mistaken or what? So I began to question, and this also brings to my mind from the physical properties that is the Dostrum connected to the upper three formations. How can I see any difference? So I started plotting other ratios and other elements. And here you can see that though the Dostrum formation forms at the base of this plot, the top three seem to want to align more than the basal one, which, though there might be a similarity or relationship between these four formations, but you can see clearly that there's a slight, if I may use, distinction between the Dostrum and the upper three. Further plots, you can see that the Dostrum begins to show something different to the upper three. In this case, you can see that the top three formations might actually look like they evolve from the same liquid, whereas the Dostrum maybe something slightly different. And I think this is why, for example, detailed work by Buchanan in his work where he tried to describe the origin of the liquids or the rocks of the top three to evolve from low titanium liquids within the Dahlstrom formation. It is clear from such scenarios that though we might want to classify these rocks together, we have to be cautious. A last plot I would like to show you, which actually nails this for me, is this here with the top three formation plotting together. And yes, again, you can see a trend showing that there's a relationship between these top three as opposed to the basal Dahlstrom formation. One good thing, another thing that I can point out with the basal Dahlstrom is you have different clusters of samples based on the type of plot you're making. And this is because in the Dahlstrom area we have different magma compositions. And now that triggers in the sense that if we have different magma compositions, which composition is the original composition of the Rooiberg group, and which is the composition that evolved the top three formations. This is part of why I'm here as a postdoc to try to investigate this further, and part of the report I'm putting together to clarify the differences. I was discussing with some people and who are experts in geochemistry, and they actually even went as far as suggesting that maybe we need to revisit the classification or the stratigraphy of the Rooiberg group. Because something, sorry to digress a bit, something also important is the Dahlstrom in the Dahlstrom area is actually different from the Dahlstrom above the Rosenberg layer suite, but that's another story. With plots regarding the trace elements, one of the things that gave me a bit of tough time is the fact that you have mantle, like we know now, signatures in the lower part of the Rooiberg, and you have crustal signatures in the upper part. Why do we have these two pronounced? And if these two are pronounced, can assimilation actually give or be the justification for these two plotting together? And in this plot, you can also see that you can't ignore a possible evidence of mixing, because you have samples, and not only in this plot, that do overlap. So yes, we have various compositions within the basal Dahlstrom, but there is mixing. And how much mixing takes place, we still have to find out. What is mixing, we still have to find out, and what is produced after mixing. And that's what part of what I'm also trying to model now. So with that in mind, can I get an idea of how the Rooiberg formed? Because I'm trying to see with all means necessary to somewhat ascertain, which has been put in my mind, that the Dahlstrom might actually be different from the upper formations. So once I started playing with models, Excel spreadsheets, and estimates from different geochemists, I got hold of Putirka's work, and I was able to get his spreadsheets that estimates pressure and temperature. And these, interestingly enough, produced increase in temperature and pressure when you're going from the older rocks and the basal rocks to the younger ones. And this is very, very uncommon. Even in the likes of Yellowstone and some other formations, you have the younger ones having a lower temperature than the older ones. And why do we have temperature increasing from the older to the younger? I started getting worried again, and I said to myself, okay, this is just one of the calculators that I use for this plot. Let me try another one to see if anything will produce anything different. And with the zircon saturation temperature, according to these authors, you can see that temperature increases also from the doldrum to the upper part. Now, how do we explain the increase in temperature, increase in pressure from an older to a younger formation? It's something very challenging but interesting as well. So I asked the question, are there any evidences that supports these geochemical signatures? And with signatures, I mean maybe crustal mantle signatures within the Rooiberg group, the magma mixing, or the increase in temperature and pressure from the older to the younger rocks. Because the beauty about geology is whenever you have a scenario, there should be an evidence or a reason for it that we should be able to support this. And in studying far and wide, which is still ongoing, I saw some works done using geophysics, and it actually makes a whole lot of sense when I look at my Rooiberg material, in the sense that we have a thick crust and a shallow upper mantle within the Bushveld province. This might actually be the reason why we have different magma compositions within the Rooiberg group, and doldrum especially. And to support this, we have mixing between mantle and crustal material during Bushveld magmatism and in the Proterozoic. So now we already have what I won't call a problem, a task to find out what is the original composition. Right now I'm busy chasing the program MELT to try to see if I can get a way to model the individual magma compositions within the doldrum formation. And during the magmatism, there was also described as a downward flexure within the Rooiberg, the Bushveld area. Why am I mentioning this? Whenever there's a reduction in distance between two bodies, pressure can be built. If, for example, in the case of a magma chamber, magma is still pumping in. And this result I used to create a model, though not completely correct since I'm still studying, that we have a shallow mantle material hosting, close to the crustal material, which probably interacted, as we have evidence for. And this started generating the doldrum formation. And with care taken, it's generating the doldrum formation with interaction with the crustal material, as we have seen or had evidence for. So if we have that, how did we form the Danval formation? We have the thick crust that is slowly reducing its distance, as we have heard that there's a crustal flexure within the Rooiberg group, Bushveld province during magmatism. Definitely, this will increase the pressure and reduce the distance between the hotspots and the thick crust. And caution thrown to the wind, the downward flexure will not only occur, as you see in this picture, from the top. It might also occur affecting the other sides if you picture it in a 3D way. So we have melting, more melting rather, producing the downward formation. And reports have been given that there are two major magma compositions within the downward formation. So yes, you do have the hotspot that is mixing with more melting or more melted material. And then you have the Shrikloop and the Quagga Snake that is composed mainly of one type of magma, which is produced mainly by melting. And this is what I could infer with all the evidences I have, that what evolved the Dahlstrom formation may not necessarily be the process or processes that evolved the upper three formation, as well as the source. So in conclusion, the upper formations of the Rooiberg group have been interpreted as Ignimbrite. And if they're interpreted as Ignimbrite and the Dahlstrom formation still is regarded as lava, there's a difference between the two. Whether it's a difference in process of formation or in classification based on physical properties, there is definitely a difference. And this difference is also evident in the fact that the mantle material, a mantle evidence or signature is more pronounced in the Dahlstrom formation, while the crustal signatures are more pronounced in the upper part of the Rooiberg group, which is mainly the Danval, the Quagga Snake, and the Shrikloop formation. Lastly, geochemical evidence suggests that the Rooiberg group formed from a combination of processes, which I believe better answers so far the origin of the Rooiberg group. I don't think a particular process will easily answer this difference in magma compositions. And in connection to that, I so far strongly believe that mixing and melting are just as important as fractional crystallization within the Bushveld province. I mean, you've seen a few results that show that the upper three formations are different from the Dahlstrom formation, and the upper three formations are similar to crustal signatures. It now makes sense why the origin of the Rooiberg group has been going back and forth with fractional crystallization and assimilation, and the evidence of the origin of subduction with related to the mantle, the crustal region. So going forward, I'm trying to model, like I said, the original liquid composition of the Rooiberg group. And by this, taking a first step, I'm trying to see how I can model the basal Dahlstrom formation. If I'm able to model the liquid, I think that would be a huge step to getting what evolved or what produced the upper parts of the Rooiberg. And for the first time also, we've been able to extract zircons from the Rooiberg group stratigraphy, especially in the basal Dahlstrom formation. And I think this will actually be something that will put some relaxation in my system, in the sense that we will be able to know which formation, which magma type, which rock type has what age. Because with the different magma compositions, there's a chance that you might have, though not too different, but similar ages. And we're already talking about age populations within the Rooiberg group. And these, like I said, might now support the person who told me that we might need to revisit the classification of the Rooiberg group. The last point, which was mentioned, we had a meeting here, is why is the Dahlstrom formation, unlike the upper three formation, confined to the Dahlstrom area? Is it structurally controlled, or is it that it's just not as much volume-wise as compared to the upper three? Because with the upper three, we have them in the Loskop Dam area, and we have them even in Limpopo in the Modimolle area. And all this area excludes the Dahlstrom formation. And if it does exclude, it goes back to the fact that there might be a different age for the Dahlstrom as compared to the top three. I already had a discussion with one of the students I worked with at University of Pretoria, And on the day I was looking at my data sets and what I've done so far, I just picked up the phone and called, do you have 2 age groups for the Rooiberg group? And she's like, I have different age groups, but in the bushveld age, I have 2 major populations. And I told her that, okay, it makes sense if I'm correct why we have 2 populations. But what I'm trying to say is the age will give an idea of what evolved first before the other, as I strongly believe, which is part of my later work, that even the intrusion of the Rosenberg layered suite actually produced or possibly produced more Rooiberg group material. Thank you.
Other questions, Olutola?
Quick question. So you define different compositional magma types
Sorry?
based on geochemistry, different magma types.
Yes.
Do you think it's a function of how much continental crust the crust materials assimilated? Or do you think it's the magma source, these magma source characteristics at different domains within the
That's a good question, and it's part of what I've discussed and I'm trying to find out using the model. Because I think even if we talk about the mantle or the crustal signatures, we need to know, for example, if it's melting, what part of the mantle is melting and how much. What part of the crust is melting and how much. And if these two mix, what is the possible ratio of mixing between these two? Because it's, though interesting, it's making it a bit more difficult that we have different lava types. And that's the bottom I'm also trying to get to.
No, maybe Susan will ask the question, but it might be a question directed to you. I always thought that the depression of the moa beneath the bushveld was related to collapse of essentially the Rosenberg layer, so the weight and thickness of that. So why do you need to invoke a depression of the crust to change the magma compositions? Why isn't it just the rising geotherm, so the blowtorch of the plume is coming through, and as it gets up to the crust, it changes? You can move the heat to there. You don't have to move the crust downwards to meet the heat source in a plume model.
Yeah.
Do you have a
Yeah.
reason?
Do you want to make a comment?
Yeah, it was sort of a question about what evidence do you have for the timing, because that's not how I would have put the timing together. Because usually a heat source will cause doming, and it's only much later when that cools that we would expect to get the crustal flexure. So I just perhaps want to discuss the timing of that and what evidence you have for that at some point.
Yes. With regards to timing, I think the dates that we'll obtain will help confine when what happened. And that's part of why I said this project, I'm involved and I'm always happy to do it. But we can't really tell with precision the timing of what happened, when the flexure happened, and like I said, this is just something I used, I read, and it applied. But now I'm trying to find the reason why it happened, just like you said.
So,
And
yeah. So I was thinking in terms of the evidence, we could use the fact that it's preserved, because if it came out on the surface and then it flexed later, it creates space for it to be preserved. So that's an example of the flexion would only occur later.
Yeah.
But we can talk about that
Yes.
in detail.
And another idea that I also came across, I don't know if it was in the same manuscript, is the fact that there's evidence for addition of material into the crust during bushveld magmatism. Now the crust has been described as thick. If you add material to the crust, it has to give, like, there should be a reaction. Now what the reaction is, we're not sure. There's a possible reaction that the crust might want to accommodate that, and I don't know if it will result.
That's what causes the flexion.
So they have a, I don't know if it's exactly the same age, but they said during bushveld magmatism, there was material added to the crust. So it might maybe happened almost, not really, but
Let's
yeah.
chat about it.
Yeah.
Okay, Sharon.
You started by telling us about the two rival models for the origin of the Rooiberg group, both by Chris Hatton. One was a subduction-related model, and the other one was a plume model. But then you also told us about the earlier work of Paul Buchanan and also Georg Schweitzer on the geochemistry of these lavas. One of the prime motivations for Paul Buchanan's detailed study on the Rooiberg organism and its chemistry was a model that was put forward by the late Professor Wolfgang Elston on the impact origin of the bushveld, and in particular of the Rooiberg fell sites. And we heard him in this room where he was standing right now before he died. He gave, in fact, several seminars here over the years, and he maintained that he had a very good argument to say that the Rooiberg was firstly the largest felsic volcanic event on Earth, and the largest volume of felsic magmas, and ultra-high temperature lavas, as you pointed out, up to 1,000 degrees centigrade and more, and so on. So this was the motivation for a lot of the work that was done here in this department by Paul Buchanan. And of course, you found no physical evidence in terms of shock or pressures or something to support an impact model. So that was a negative thing. So what I want to know is there any further developments in terms of this? You didn't even mention this model, so I presume that the Pretoria group has basically washed their hands on this model and are not thinking about it anymore, because they're not even trying to disprove it or prove it one way or the other. So, but I don't think that model has been disproven in any way completely, and you should be thinking about these things, because what you've shown us from your data is that we're seeing evidence for huge amounts of crustal contamination to produce upper volcanics. And that's one of the things that Wolfgang Elston talked about in his model. And you should not dismiss it completely, because it is, he has produced some very compelling pieces of evidence which have not yet been refuted completely. This is what I want to say.
Okay, thank you for your comment. Can I just move up? Do you want to say anything there, or kind of want to add?
I just want to say thanks for pointing that out. When I started, I bumped into a figure in the sense that they said the Rooiberg group is having a volume of more than 300,000 cubic or square kilometers, an area of 300,000 square kilometers. And I tried using some of these models to see if I can generate, with discussion with people in the field, if I can generate such huge volume via impact. And before they even try to welcome my discussion, they're like, really? So I'm not saying I put it aside totally. I'm not saying I put it aside completely, but one thing I'm also trying to do with the models is, if I can also get, it's what I'm also trying to speak to Grant, if I can, you can teach me how to use the, for example, the mails, like if I can model this origin, because believe me, I know I didn't mention it here, but it's science. You can't put everything away, but if I can model that impact can actually generate this much, because especially the upper part, it's so huge. I was asked the question once, is the Dahlstrom same volume as the upper three? Based on the area that I've worked on, I can't tell you which one is greater. So, but for that huge volume, I'm not sure if impact can. And somebody asked me, what if there's multiple impacts? I'm like, we now need to find evidence for multiple impacts, but it's a study going on.
Before you answer your question, can I just jump in and ask a question? In your very early maps, you showed the extent of, can you bring up a map for me? I think it's more or less your first map.
Yeah.
What is the evidence for the occurrence of these Rooiberg rocks way out to the west and south of Pilanesberg? Because we calculate volumes on this, and I think this map is from Johann Kruger,
Yes.
and he's copying something from 30 years ago, and I can't find what the evidence is for Rooiberg lavas or Ignimbrites around much of this western area.
One of the things I said earlier is the Rooiberg group has been proposed to have about 300 square kilometer area, and it doesn't seem to be easily accepted, or I don't easily believe it. And that's why I started mapping several areas in which the Rooiberg is observed, hoping to get to some of these areas you talked about. Then I would have been able to give you an idea. But with regards to that, I don't have any much idea about the areas even that I haven't visited. Like I was discussing with Paul and Lawrence, someone found badeliite in this region. Oops, sorry. In this region of the Dahlstrom.
Right.
And he only found 2 samples, and that's why I also spent days looking for badeliite. So what I'm trying to say is a lot of things are still not as straightforward and possibly not as accurate as a lot of us will want. And that's why it's always necessary to go or continue mapping and see if
Because
it's...
that seems to be a map that's copied from something 30 years old, and I can't see. Right, last question.
One of the things that's very characteristic of these rocks is extremely big negatively roping anomaly. And you don't show any evidence of magma chambers in your model, which is really the only way you can get a negatively roping anomaly like that is by massive separation of plagioclase. How do you explain that?
This is just an aspect of my thesis. I actually have evidence that within the Dahlstrom, which is almost absent in terms of the European anomaly, it starts forming as you go upwards, similar to what Buchanan found, which is typical of plagioclase crystallization. And in the graph I showed you, I forgot to mention this, about the increase in temperature and pressure. It's from plagioclase I was able to find that, which is evidence of fractional crystallization. So I'm not saying that fractional crystallization is absent. I'm just saying that you can't call or name fractional crystallization alone and assimilation, because even if you talk about assimilation, how much material are you assimilating to produce that huge volume in the Skrikloof, Wakkersneck, and Danval? And that's the big issue. So with me, so far, the evidences I have, just as much as you pronounce fractional crystallization, I think you have to pronounce the other magma mixing and or melting.
Okay, I'm going to end it there. Thank you to all of you for coming. Thanks to John Hancock's CCIC Coal for the drinks and chips. And thank you, Tola, for your talk. I'm sure if anybody has any discussion points, they can find Tola on the top floor. And good luck to you, to those of you who are facing exams at the, in the not too distant future. And come on Friday for Chris Hall's talk. Thanks a lot.